Welcome back, geochemistry fans. In our last episode, we met boiling water and the kyanite, andalusite, sillimanite system, with which we described invariant points, univariant curves, and divariant fields. But both of these univariant reactions take place at a given pressure and temperature and consist of both reactants and products. These chemical reactions are called discontinuous or univariant reactions. But what if I threw salt in the mix? Salt water has two components, H2O and NaCl. Now the temperature at which this salt water will boil is not solely controlled by the pressure. The phase rule tells us we still have the two phases, but added a second chemical component to give us a second degree of freedom. If I plot boiling temperature versus salt concentration, I have to specify the pressure for the line. This is for 1 atmosphere of pressure, about 1 bar. So we have three variables: pressure, temperature, and overall concentration of salt, and 2 degrees of freedom. We no longer have a univariant or discontinuous reaction, but a continuous reaction. These reactions have another degree of freedom, with reactants and products coexisting not at a set pressure and temperature, but a range of pressure and temperature in a divariant field instead of a univariant curve. In minerals, we will meet several phases that can exist as solid solutions, such as micas, amphiboles, and feldspars, and the variation in their compositions can add this extra variable needed for continuous reactions. Should a mineral reaction involve no growth or loss of mineral grains, but only change in their composition, we can get a special kind of reaction called a cation exchange reaction. Common cations that get exchanged for one another are ferrous iron and magnesium, potassium and sodium, calcium and magnesium, and 2 sodiums for a calcium. In cation exchange reactions, 2 or more minerals in a rock can swap these ion pairs with each other. Some crystals prefer one flavor of an ion over another, and in the iron-magnesium system, garnets prefer magnesium over staurolite, which has more magnesium than biotite, which has more than chlorite, which has more iron preference overall, obviously. As temperature increases, crystal lattices get a bit looser and have a harder time segregating one ion over another, and the various minerals take on more equal levels of cations with increasing temperature. Pressure, temperature, fluid pore pressure, and chemical composition, including these cation exchange reactions, are all separate variables. But how many get to be represented by F in the phase rule? How many of these variables are truly independent? Usually only one to a few at most. This can lead to another chemical concept we call buffering. Going back to our boiling water example, it buffers a temperature at a given pressure for the time that both liquid and gas phases coexist, 100 degrees Celsius at 1 atmosphere pressure. It doesn't matter if I boil this quickly or slowly, the boiling temperature remains 100 degrees Celsius until all the liquid has turned to gas. The temperature was buffered in that reaction. How about a more mineralogical example? We met hematite in the oxide mineral episode, which is basically iron rust with the composition Fe2O3. In the same episode, we also met magnetite, the magnetic mineral made of Fe3O4. As it turns out, we can turn one of these minerals into the other, using this balanced chemical equation. Let's say we are turning hematite into magnetite as we descend into the earth, which commonly happens. The oxygen expelled in the reaction goes into the fluid phase, and we can speak of the portion of the fluid pressure that this oxygen exerts as being a fraction of the total fluid pressure, and this thermodynamic effective pressure has been given the term fugacity, which is another way of measuring pressure, partial pressure in this case, and so is reported in the same units we've been using, such as pounds per square inch, atmospheres, and bars. Using the phase rule, we see that there are 3 phases in this reaction: hematite, magnetite, and oxygen. And we can make it from these 3 chemical components: water, FeO, and O2, resulting in 2 degrees of freedom. This means that even though the fugacity of oxygen in the pore fluid is a variable, if we were to set the temperature and pressure of the system, this fugacity can't be any value at once. It gets nailed in as a dependent variable, just as the temperature of boiling water gets nailed in at a given pressure as the boiling reaction continues. Here we see oxygen fugacity increase as the reaction begins, but slow then stabilize to a value set by the pressure-temperature conditions, and the hematite to magnetite reaction proceeds no further. Only if the pressure or temperature changes, determining a new fugacity of oxygen, can the reaction proceed in either direction. And while we're swimming in these fluids, we should note that this reaction and many others in metamorphism act to expel volatile fluids such as oxygen, but mostly water and CO2. With less severe metamorphism, we might see methane being released by reactions, and in generally rare cases, maybe nitrogen or hydrogen. Reactions releasing these fluids are called devolatilization reactions, and as we saw with our buffered iron oxide example, the release of these volatiles is dependent not only on pressure and temperature, but overall fluid pore pressure and composition. Too much CO2 in the fluid inhibits CO2 release from mineral reactions, and overall pore pressure generally reduces these reactions. Of course, there is a limit to which fluid pressure can build up, that being the lithostatic pressure plus the rock's tensile strength. At that point, we get hydraulic fracturing, and the fluids tend to flow out through those fractures. In most theoretical and experimental cases, though, the fluid pressure is just about equal to the lithostatic pressure. In fact, right as metamorphism begins, water and CO2 get released and fluid pore pressure begins to rise up to lithostatic pressure, so very few reactions in metamorphism take place with fluid pressures below the ambient lithostatic pressure. Our iron oxide reaction also demonstrates another chemical aspect, that of redox reactions. I mentioned this type of chemistry last, as usually there is little to no oxygen available deep in the crust to participate in our metamorphic reactions. The amount of iron in a mudstone might stay the same as it is metamorphosed, but often the amount of ferric iron goes down as it turns into ferrous iron, which increases. This is due to oxygen being driven off in reactions like the one we've just been looking at in this episode, and then escaping the system as a fluid. The hematite in our reaction can also get reduced when it comes in contact with organic carbon, as we see in this balanced formula. And this is why an organic rich sedimentary rock may end up with less carbon than it started with as metamorphism proceeds, again because the CO2 may escape the system as a fluid. It should not be news to us that scientists don't like giving all the long, flowery, detailed descriptions I use to communicate science. We prefer shorthand notations such as these formulas that we've been playing with. But spend some time with a scientist and you're going to end up looking at some graphs. We already saw this graph for the kyanite andalusite sillimanite system, which is what we call a PT graph, on which every point is a distinct pressure and temperature. We see it as easy to plot a single composition changing polymorph mineral form on this chart, but if we want to investigate several components in even more phases, such a PT graph gets too cluttered and unreadable. To get a better handle on the effect rock composition has on mineral equilibrium, we turn from the PT diagram to use a compositional diagram. In this case, we need to choose a specific temperature and pressure and plot out the stable mineral forms that might appear on this compositional diagram for those conditions. We can't choose any temperature and pressure, as these diagrams are made within divariant fields and avoid univariant curves and invariant points. The simplification being used here is that when you're in a divariant field, there are 2 degrees of freedom, and as we can see from the phase rule, in that case the number of components is equal to the number of phases. Let's say we are looking at a chemical system with 3 main components, CaO, SiO2, and Al2O3. With 2 degrees of freedom, we know that there should be 3 phases to balance these 3 components. We place these 3 components on the tips of a triangular compositional diagram like so. Recall that these compositional diagrams are for a particular condition of pressure and temperature. So let's say that we go to some arbitrary pressure and temperature such that these compositional elements will be possible to make corundum and aluminum silicates such as those in the kyanite, andalusite, sillimanite system, quartz, calcium plagioclase, which is also known as anorthite, grossular, and wollastonite. If we connect all the mineral phases that can coexist, we end up with this plot. The lines that join minerals can reach equilibrium together and are called tie lines. We noted that we have intentionally chosen a pressure and temperature condition that has 2 degrees of freedom, and thus the 3 chemical components will result in only 3 stable mineral phases here. Every triangle we can identify on our compositional diagram represents a possible stable mineral group for that pressure and temperature. A parent rock of one chemical composition may end up with minerals of corundum, grossular, and aluminum silicate at this pressure and temperature, while another rock composition will end up with grossular, anorthite, and quartz. As tie lines connect minerals that can exist stably, we know that any minerals not connected directly by a tie line cannot coexist stably, at least not at this pressure and temperature. At the conditions for this particular chart's chemistry, pressure and temperature, corundum and wollastonite can never occur together. Though discrete minerals plot as points on a compositional diagram, solid solution minerals can plot as lines or even areas, and it should be obvious that though 3 components are quite manageable on this type of plot, more than 3 will start to get complicated. We may be able to use projection of points from a 4th parameter, or you give up trying to plot this in 2 dimensions. But I'm just trying to give the basics of mineral chemistry, so we will end by noting that not all reactions happen right at univariate curves. Many of these mineral reactions overstep their reaction lines so that a mineral that should be unstable might persist to higher metamorphic grades or even lower metamorphic grades. And going to lower metamorphic grades will be important, as any metamorphic rock we hold in our hands must have been uplifted and eroded to the surface, and thus go through progressively lower temperature and pressure to get back to 15 degrees Celsius and 1 atmosphere of pressure at the surface. If mineral assemblages changed instantly at their reaction lines, we would never see some of the minerals produced deep in the earth. They'd all retrograde back to surface conditions. So when we come back next time, we will take a look at the changes that take place in the first of our metamorphic rocks, the non-foliated metamorphic rocks, here on Earth Explorations.